Matthew received his PhD in 1984 from the University of Michigan in microwave electronics. From 84 to 90, he worked at GMI E&M Institute as a senior scientist with Hughes and McDonnell Douglas. His area of specialty has been millimeter wave research and development. He's worked on millimeter wave noise sources, calibration procedures, and measurement equipment. This result has resulted in 2 patents and numerous papers. He's currently a professor at CSUN, and he's our chapter chairman. Matthew.
Thank you, Brad. Thank you, Brad, for a nice introduction. Good evening. Today's talk, as you already may know, is on millimeter wave noise measurement systems and using solid state noise sources. Let me just tell you up front. The only new thing about it is solid state noise sources. The rest of it is just, common knowledge, which I'm bringing it out, accentuating certain areas of it. So that's the honesty up front. The talk that you will see tonight has a number of parts I'd like to go over with. First of all, the importance of noise. Why is it that we like to talk about noise? The second area is we're going to talk to you about the millimeter wave noise measurement, a general setup, a basic setup. What does it look like? And then how we can convert it into a millimeter wave later on in section 4. In section 3, I'll talk to you about noise sources, primarily the newest technology, which is the solid-state noise sources, are millimeter waves. And section 5, we'll talk to you about the uncertainties involved, because noise measurement is a very precise type of measurement. You just cannot go into the lab and throw in your noise generator and make a few measurements come out. It doesn't work that way. So based on that, I have a caution for everyone. I hope that this caution will work, because as I was indicating to you, it's slightly more than just making a quick measurement. We don't want anybody on our lines who is quick but showy. So I have this little slide for you to caution you about about the split positions. We don't want them amongst ourselves when we're making the measurement. Now, let's go back on the serious side of noise. Why noise is important? That's perhaps the important question. Before we can really answer that question, the important point is to define what noise is. Then we can deal with it. The best way I can define it for you is to tell you that noise is an internally generated interference that a receiver or an amplifier generates as the signal is going through it, which basically, as a result of that, degrades the performance of the component or the device, or whatever the case may be. To get that point further across, let's take an example. Let's say you are on the beach, which is not very commonly, easily can be visualized, nearby. And let's say you're looking over the horizon and you're seeing a ship, and you're trying to make out the flag and find out what country this ship belongs to. And let's say that you have a telescope. You have 2 of them, actually. One of them, the one that you are trying to look through, is the first one, and is relatively cheap, jerry-built, and it's got scratches on the lens, and it can't be focused easily. So when you look through it, you see a very fuzzy picture of the ship. And you see somebody standing on the deck, barely can see it. And you take the second telescope, and you look through it, you see a clear, focused, sharp picture, and which brings us to this diagram here I have for you here. Very sketchily drawn, but you can see what I'm trying to refer to. You see very sharp focus, and you can even, if you're really curious, you can even make out the captain's beard is red. So that would be a kind of the idea of noise, the same way as this coming across to you. Now, how would noise compare with this example? This is more tangible because we're using our eyes as the receiver. See? In actual electronic systems, we have a receiver which sees a signal. And the signal comes in, it's amplified, also noise gets added onto it. Now, one thing we should recognize is that the noise added by the amplifier, it greatly increases the cost of the overall system. Now, this may not seem at first glance to be the case, but let's take it one more step. Let's see if we reduce the noise, what do we really expect to see? Let me go over three things that may be able to do if we reduce the noise on it. The first one, we can have obviously wider repeater spacing between the two relay stations if you're relaying the signal between 2 points. The next one is the transmission power. Obviously, you can reduce it because you have less noise, therefore you can reduce the transmission power so that you can get the same signal to noise ratio. And the third one, obviously, you get better sensitivity to weak signals because your noise floor is lower, therefore you can have smaller signal and you can still detect it. And all these three things obviously reduces to one thing: money. And in case you were, happens to be your favorite topic, I think you're talking about on your wavelength tonight. The economic return. That's what it boils down to. All of these three things saves you money, and I feel like that's the kind of a talk you're going to be getting tonight. Now, let's talk about a moment about origins of noise. What and where the noise comes from. There are two sources, obviously. One is the noise that gets added to the propagating signal as it goes between 2 points, or the other type of noise would be when it's generated within the receiver system. Now, this is our topic tonight, but let me go over very briefly what this one is. The noise added to the signal, propagating signal, is of two types. One's atmospheric noise, which is due to oxygen absorption or humidity in the air, and the other one is the EMI noise due to man-made generation of noise, such ignition or computer clocks. Any digital system has these clocks and constantly radiates. So these two are contributing to the noise. The important part is we cannot control these two. But this one, we can. And that's what we're going to be after, basically, to remedy the noise generated inside the system. Now, let me give you a very brief idea about what the atmospheric noise is. This is the famous bathtub graph. And interesting point about this graph, it's got two local maxima at 61 and 94 gigahertz, which happens to be the favorite frequencies for the military field communication, because they have the highest absorption at these two, and they can therefore communicate in the field without being detected. On the other hand, for most commercial applications, we are in this area between 1 and 10, even here, for Ka, even Ka band used, but still in a low noise or a lower absorption by the environment. This is basically not our topic. I'm just trying to tell you what we're not going to talk about, so that you know what the area is. The area I would like to talk to you tonight is the receiver noise. That's the area that we can basically work with. Any receiver you pick up has two types of components, obviously. One is active, one is passive. The first one, the passive components that you have, they are generating thermal noise, primarily. And the active components generate three types of noise: thermal noise, due to the room temperature you're in, or any kind of environment you're in. The shot noise, that's more like the active devices when the electron is randomly going through the active device, like for example, PN junction or transistor, or Schottky barrier diode. You have a drift electrons across the junction that will give you the shot noise. The flicker noise or the 1 over F noise, that's more like due to injection of carriers across the junction. So both these three contribute to the internally generated noise within the receiver. Now, the best way to characterize noise is using a commonly known term called noise figure. Now, noise figure relates to all system levels. You can have a noise figure spec for a system, subsystem, subassembly, the amplifier module, or a device level. And once you specify your noise figure spec, then you can break it down for every device within that system. What should the spec be? Therefore, it's commonly used independent of any other parameter. We can specify what the noise spec should be. So let me define this before I go any further, because noise measurement is really meaningless when we don't know what we are measuring. See? Very difficult. So the first thing I like to define for you is a noise figure. The definition of it, some of you guys may already have run into it. It's very simple. It's a signal to noise ratio at the input of the device, right here, to the signal to noise ratio at the output, which is right here. Obviously, the signal to noise ratio at the output has been degraded because of the noise added inside this receiver or the amplifier. So the result is a number more than 1. So I'm showing you here another way of showing it, 1 plus NA. NA is the noise added within this receiver divided by KT naught B. That's your input noise floor due to this thermal noise from the source termination times the gain of the amplifier, KT naught BG. If NA is 0, your noise figure is 1 or 0 dB. That means you have a perfect amplifier. You rarely see it, but that gives some idea of what we're talking about, which is noise figure. This can be converted into what we call a noise temperature, an equivalent number called noise temperature, which can be easily done. All you got to do is just convert this noise added in the amplifier, bring it to the input side. Then you can have another resistor here at temperature TE, while this one is at temperature T naught. And then the amplifier becomes a perfect amplifier. In that sense, then we get noise figure becomes 1 plus T over T0. Now, noise temperature is not common unless when you have your noise figure is very small. Then you start using noise temperature. Normally, noise figure is used. It just for some of you guys who may not know which one do you use when. The other two comments I have for you with regard to noise figure. Number one is that noise figure is a fictitious figure of merit. It doesn't really exist in the same sense as current voltages. It doesn't really exist. We define it to basically identify what kind of component do we have. The second point is that noise figure again is unique, independent of all the other ones that I already talked to you about. Doesn't depend on bandwidth or the gain. Only depends on noise added within the device. Now let me give a typical, a few examples of commonly heard or seen devices and components. Let's say bipolar transistor. Here you have about 1 dB noise figure, about 4 gigahertz. Of course, this is daily. I mean, I shouldn't say daily, but one thing maybe changes. These limits I'm showing you here, the bipolar, of course, you can go up to higher frequency, but this is commonly commercially available. FETs, on the other hand, have a higher frequency range in terms of performance, and they outperform bipolars at the higher frequency. The broadband amplifiers, for example, obviously they must have a higher noise figure because they are built up of many devices. And therefore, they have higher noise figure compared to bipolar. A mixer, single sideband mixer, similarly has about, let's say, 6. These are all typical numbers. I'm just showing some example of how noise figure can be used in characterizing a component and find out how good it is. Now, an example of a system noise performance that you may have already seen is, let's talk about a commercial satellite doing a simple transmission from the sky down to ground station. This is about maybe 20,000 miles above the ground station and transmitting down here, and being received here. What I'm showing you is a typical example. Let's say the signal being transmitted is 40 dBm at the transmitter power, and the gain of the antennas are about 15 dB. So if you put them together, you get about 55 dBm ERP, or the emitted radiated power, from the antenna. Path loss from the satellite to the receiver minus 200 dB. Your antenna gain at the receiver is 60 dB. You end up getting 185 dBm. That's your power to the receiver. That's the weakest signal. Let's talk about noise. What happens to noise at the receiver? We want to find out what is the noise floor. The noise floor at 290K per hertz is minus 174 dBm. Your bandwidth of the amplifier is 100 megahertz, so you have 80 dB in bandwidth. Your noise figure at the receiver is 5 dB. You add them up, you get minus 89 dBm. That's your noise floor at the receiver side. So your signal is minus 85, and your noise floor is minus 89. So you have a 4 dB link margin. So if your signal is going to be seen, this is your sensitivity. It has at least has to be more, at least 89 or more, to be received by this receiver. If you want to increase it by 3 dB, the margin of the of the reception signal, you have to do 3 things. Either increase the power of this one by 3 dB, which is double it, or increase the size of the antenna on the transmitter by 3 dB, or the easier way around it would be to increase, or decrease rather, the noise figure by 3 dB here. This is what we're going to talk about now. Increasing this is easier than increasing the size of the antenna or transmitter power, because they are limited on the sky, their weight, and a lot of consideration comes into it, and the cost of maintenance. We cannot change this much, or we can change this much. So what we're going to concentrate tonight, we're going to talk about ways of measuring this, ways of reducing it, and also making very accurate measurement, because it happens to be very important to measure a signal here above the noise floor of the receiver. Now, the basic measurement strategy, let me tell you what it is. It's very simple. You sometimes run to read some books and get totally confused. I mean, I've been through it myself. So I want to make it very easy. The noise figure measurement is extremely simple, theoretically speaking. Theoretically, let me qualify that. What do I mean by that? Then the source resistor, or source termination here, let's say has a range of temperatures on it. If we plot a source temperature Ts versus the noise power at the output N, if we plot this, when the input noise is 0, we still have amplifier noise added on, in NA. If we change the Ts above 0, we get a line. So this line shows you basically the noise figure variation versus temperature of the source, where the source wants to be. So to make a measurement, all we have to do, we have to make 2 points on this line known. Once we have 2 points on this line known, then we can measure the slope and the intercept. Now having those two, we can find the noise figure. So any measurement setup that you want to create, you want to shine or inject, or however you want to call that, two different powers. Either hot, cold at this source termination, or if you want to use a noise tube or any other noise source, on off will give you N1 and N2. Those two noise output powers will give you 2 points on this line. With the help of little microprocessor or little hand calculation, if you wish for manual measurement, you can easily find out your noise figure. So your basic measurement setup has to consist of very easy blocks. A noise generator. Why a noise generator? Well, any measurement setup has a generator. You all know that from basic electronics, right? For a noise measurement, we need a noise generator. Easy so far. The next part, an attenuator to perhaps change the power coming out from the source. And then device under test. And this part right here is a frequency conversion stage, which you may not need it if you are working on low frequency. However, at limited wave frequency, you almost always need it because your power detector and meter are low frequency stuff. You always have to convert it to get to their range of frequency to be detected. Therefore, this stage is always in at millimeter waves. For microwave measurement, let's say HP 8970, you can go up to 1600 megahertz frequency. So if you're making a measurement below 1600, you don't need this stage. If you are making more, then you have to definitely put that in to make the correct frequency conversion and the correct numbers in the process. So remember this basic setup, because I'm going to take this basic setup later on and expand on it, make it look a little fancy, a little complicated. I hope that you stick with me and track with me on those. All right, the important part of the, let me put this back on again for a moment. The important point of this setup, the components are very easy to protect. Attenuator, well, not much to it. This is the one we're interested in, noise generators. If this is accurately calibrated, it can save us a lot of hassles in accuracy. And we're going to take this one and talk about this one first, and then we're going to take this whole setup later on and put it into millimeter wave format. The rest of it, this power detector and meter obviously has been replaced recently, or for a long time, I should say, with noise figure meters. So they do the job. And even these parts for low frequency measurements are inside this box. So what you really have to worry about then this noise generator aspect of it. Noise generators are, at microwave frequencies, can be classified into three categories, I should say. The first one are thermal noise sources. You may have heard of it. Hot, cold, standard. They are very accurate. They work at, they take basically a source termination, a simple resistor, they put it in liquid nitrogen, 77 degrees Kelvin. For T sub C, the low power part. The high power part, they put the same resistor in boiling water, right? That's again accurate. All these temperatures are very accurate. Therefore, you have two exact point powers, because the water always boils at 373 degrees Kelvin, and the nitrogen, liquid nitrogen, at 77 degrees. So therefore, you have two exact points that doesn't change, and therefore, this are maybe in the old times. I know some of my colleagues, it's beyond my time, I should say. Some of my old colleagues will tell me about that. They used to do this technique for regular measurement. It's no longer done. This technique actually is done only for calibration houses now. Like primary cal labs, they can do this because it takes a lot of time and it's very tedious, and it takes, like my colleague was saying, it takes 6 weeks to make one measurement. I mean, can you even imagine the time involved? So this is not really a commonly done technique of measurement anymore. It used to be maybe 30 years ago. It's just used primarily for calibration houses. This area again gas discharge noise tubes is just becoming obsolete, just on the verge of becoming obsolete because of more modern sources coming out, which we'll talk to you tonight. The gas discharge noise tubes, they are basically high temperature tubes. They generate white noise, which is a constant spectral density over a large frequency range. They need a modulator. Remember, we need to turn it on and off. The noise tube, they don't turn the noise tube on and off, they turn the modulator at the output of the noise tube on and off. Therefore, they can show like two different powers, N1 and N2, a modulator. ENR of a noise tube is about 15 dB, approximately. It varies. I'll show you later on a little graph of it. Now, this technology is currently being replaced with this technology here, solid-state noise sources. I will talk to you tonight in more detail about it, but let me give a few characteristics about what they are. They can create a very high output ENR. Now, ENR means excess noise ratio. That is the amount of noise above the thermal noise. And I'll define it for you later, but remember the excess noise ratio is the term used when we talk about noise generators. Because of the high output ENR, we can afford to waste some. How do we do that? We put a 10 dB pad in front of it, and let's say we have 30 dB ENR. Let's just say that. So we put a 10 dB pad in front of it. Therefore, when the noise generator or the noise source becomes on and off, the output of the 10 dB pad will not see much of a change in VSWR. Therefore, the mismatch error will be reduced. That's why I have a low on-off VSWR. Also have a low mismatch error because of the same reason. And finally, in case you didn't know, use the impacts. Now, what are the impacts? That's the question I'll talk to you tonight. Bear with me, we'll get to it. Let me give you a very brief review of the technology of noise tubes. You already may have seen this diagram, but just let me review it for you. The noise tube basically consists of a tube mounted in a waveguide. This is a waveguide I'm showing you. A waveguide mount at 10 degrees, shallow angle in the E plane of the waveguide, which would be the plane through the middle of the waveguide. You have a termination at the end which absorbs any power going that way, preventing any deflection. The power coming out goes outwards from here. An important point to remember about noise tubes is that they take a very high voltage to create gas discharge, about 1,000 to 5,000 volts. And they draw a large current, 100 milliamps to 200 milliamps. So you can imagine the power supply required is not an ordinary power supply. That is one of the biggest drawbacks that these have, because the power supply, you work with them, they're awfully heavy. You can probably see it. It's not an easy thing to work with. So that's one of the biggest drawbacks that you have in the noise tubes. You also have the idea of they're very bulky, very fragile. Inside this tube you have some kind of a gas, argon, neon, sometimes xenon, all of these. And every one of them will give you a different ENR, depending what the gas you use. But the idea here is, again, you gas discharge inside here and the noise will come out. Now let me show you an actual noise tube assembly, because these are not used by themselves in actual practice. What we really have is we put them in a box. It's an assembly of it. Here's the noise tube. And here's the output right here. The goes right through here. An isolator that isolates for on-off. It goes on and off. This prevents any mismatch. The VSW at the output will remain relatively constant. And this is your modulator, which turns it on and off. Now, if this is always on, this will create a high loss or a low loss, so it makes it look like on and off. Of course, then you have the terminal for high voltage coming in. This shows you what inside one of these boxes are. Now, let me take you to more modern stuff. This is like, like past time. Now, here we go, solid state noise source, which is more popular. And actually myself, one of my colleagues, some of you guys may know Joe Cadwallader, we helped to design some of these at millimeter wave, one for K and one for V band. And they're still being used. They have not been obsoleted yet. I don't know of any other technology yet to come out and obsolete these. These sources use an impact diode. An impact diode is relatively easy. It's a simple p-n junction. Except you got the P plus, which is heavily doped semiconductor here, not an N plus. This region right here is slightly different than a normal diode. What you have here, to create the avalanche breakdown, you need a heavily doped, relatively heavy, not as heavy as N plus doped, and the rest of it lightly doped. What really happens in that process, if you reverse bias this junction, this is a P plus N, so you put a positive voltage here and negative voltage there to reverse bias it, obviously. You have to avalanche breakdown. The E field inside this area would look at a profile like this. Mostly would have a highest E field here at this area, particularly the active region. That's where your breakdown is going to take place. The E field here is more than the E critical required to break down. Therefore, this area will break down, okay? And the result of that, number of electrons generated, and the electrons drift in the E field, opposite to the E field, and will be collected at the other end. Okay, so you have, as a result of avalanche breakdown, you have a large number of electrons generated, which drift, and that's where the term transit time comes from. The transit time come here, and the avalanche will create the electrons to impact, obviously, of the high collision. Now, ordinarily, all these impacts are used for amplifiers. But if you have had the experience of working with them, they're very noisy. So we put them to what they want to produce, noise. So we just put them right there to create the noise for us. And use these, you have to, of course, do it correctly, right cavity to create the noise. But the idea again behind it is using avalanche to create the noise, which will then later on be picked up and transmitted. Now, you may be interested to know in actual practice how these diodes generate the noise. What kind of a spectral density function are we looking at? Well, I'll not bore you with the mathematics on it. I'll just give you a very idea of what this diode is doing. You plot power, the spectral density versus frequency. You see at F equals to Fa, at this frequency, has the highest amount of noise, theoretically speaking. Fa is a constant, because noise frequency is a function of the current, inverse proportional to the cross section of the diode, and the breakdown voltage of the diode. Now, if you look at this diagram, we see three regions, distinct regions. One is this area right here, F much smaller than Fa, right? Which the output power is relatively constant right here. F much smaller than Fa. Then we have this area right here, F equal to Fa, which the diode blows up. But that's a theoretical misconception because it doesn't really happen in actual practice. In this theory, we assume the diode has zero resistance. In actual practice, you have an internal loss of diode who will give you the peak, but not infinity. See, that's the major difference in the theory and practice. And then you have out here, F much bigger than Fa, where you have almost no output power. And you may wonder, where do we use this diode? What region of this graph do we use this diode? What's it lends itself best for a noise generator? That you guessed it right. It's right here. Where F is much more than Fa has a relatively constant output power. To get that kind of a thing, means that you have to push this FA large out here to the right. And to do that, that means normally you don't want to increase the current, because increasing the current means you're heating up the impact. You don't want to do that. You want to increase, or decrease rather, you want to decrease A, cross-sectional area, which means the capacitance, and the breakdown voltage. So the ideal diode would be a diode with the least capacitance, which is about 0.7 to 0.9 picofarad at that frequency, at the millimeter range frequency, and dB anything between. Normally at millimeter wave they have about 7 or 8. You're lucky if you can get 7 or 8. And that's, so based on those two criteria, you pick the diode. That's the main criteria you have to operate. Lowest capacitance and the lowest possible breakdown voltage. Then in that case, this will be pushed away and we're working in this area if we choose the right FA. Let's say I had a design, I'll show you later on, I chose FA maybe 100 gigahertz out here. Then I had a cavity working about at Ka band, 26.5 to 40 gigahertz. So that's an example of it. That's how you can get a relatively flat output noise power. Now, how do you package these devices? That's just a very brief history of it. You may be interested to know how these diodes are really made. Well, you start with a simple metallized diamond at the heat sink. You use diamond because it has the highest thermal conductivity, better than copper even, at room temperature. So you use diamond and you solder it to the heat sink. You get this kind of a configuration, and then we bond the diode to the top for heat sinking properly, and then do the ring around it and with gold ribbons, and finally the cap. So you have this simple little, almost a flat surface with a little protrusions on the outside, but very little coming out. These ribbons, the gold ribbons here, are important because they are basically giving you parasitic inductance. The question is, how do we reduce the parasitic inductance of these ribbons at millimeter wave frequency? Any piece of length of wire, as you know, is an inductor, right? And so we have to reduce it. Let me give you an idea here what that may be. Jump ahead of myself. What I have here is that a simple showing you different possible bonding here. Half strap, only half of it, and full strap will give you about 1.23, and cross strap 0.06. That's the most commonly used. So all our diodes that we are experimenting with and designed for cross straps with the least inductance. The cross-sectional area will look something like this. Of course, these are way enlarged. They're so small you can't see them with your eye. But this shows you simply you have the heat sink, the diode here, and the ribbon, you have the ring, insulator ring around it, and then you have the cap. Now, of course, the heat sink, this thing extends outside, it's not shown. It's a slab with a blue diode on top of it. Now, once we get the diode, what do we do with it? That's the important question. What we're going to do with it, we're going to put it in the cavity. Now, the cavities that experimentally what we're working with, there are three types you can run into. One is the full height, let's say V-band. Full height, both ends of it, and here's your diode here. This is the bias pin. The load is placed at the end. Normally, these cavities, when they're loaded with an impact like that, at the output, right here, they put short. They don't put the load. They put short for oscillation. oscillates better. However, for noise generation, we don't want it to oscillate. We want it to create noise. And that's what we put a load here. It's very important because I found out early on in our experimentation that a short would definitely create a situation where you have noise in part of the band, then you have oscillation, and then you have noise. So it wouldn't work. And you have to have the load. And the position of the load is extremely important. That's what gives you the flatness that you need for a noise generator. The second type of cavity is full height, reduced height, and finally you have a transformer, which makes it a reduced height and reduced height, so RHRH. Amongst these three cavities, you can probably take your own guesses. This one outperform more the other one. You can probably guess, right? And that is because of these little lines there with a little transformer there, which gives you a better VSWR and better output noise flatness over a full band, let's say, from 50 to 75 or 26.5 to 40. And the load again is always there. And simple, the coolant circuit for this, if you want to put it down, electrical currents, how does this thing look like? If you have this transformer here at the output, as I showed you for a reduced height cavity, then you have the two DC blocks, which can be obtained through the bias pin. You have the impact, is parasitic capacitor, and the inductance here. Then you have the pin having an inductance. And L&C is your cavity. Cavity is an oscillator. And then finally you have the termination, which absorbs any power coming its way when it reflects and oscillate. In order to bias this, obviously, we have to get our input from the noise figure meter, PNC input, 28 volt, that are already there. We go to a little DC current regulator and RF choke to prevent any RF coming in, goes to the impact. This is simple, showing you, in essence, what is a noise generator at solid state is going to consist of. A simple configuration. We built this whole thing. Of course, we did a lot of other things, but this is what came out of it. What we really have as a result of this, we have the PNC 28 volt coming in, feeding into the circuit board. Right, you can see that the circuit board is your circuit board for a DC current regulator. Creates a constant current because impacts require to have very, I should say, stable and regulated current through them to generate a constant noise output. So we have to have this little circuit board to act like a power supply, and then the output goes to this spring mechanism, which will feed down to the impact sitting here, and the output